Alright, hello everybody. Tonight we're still going to be working on TensorFlow, but rather than going through one of the Google tutorials, instead I'm going to attempt to implement the Mahalanobis Distance metric in TensorFlow. I'll try to explain a little bit of what that is. It's something I have a little bit of familiarity with, but not a lot. So I will be doing a little bit of learning along the way. I forgot to open Firefox, so let me do that. And we'll keep the Wikipedia page for Mahalanobis Distance open. Mahalanobis Distance, there we go. Ultimately, our goal is going to be able to match SciPy's built-in Mahalanobis Distance. It's the Wikipedia would like you to donate today. Today is Giving Tuesday. Right. So what is Mahalanobis Distance, first of all? Let's step back. Normally, if you're in the XY coordinate plane and you want to know the distance between 2 points, you typically compute what's called the Euclidean distance. So you take you draw a straight line between those points and you get the distance of that. And you figure out the distance of that line by taking the difference in the x's squared plus the difference in the y's squared, add those numbers, and take the square root. And if you have more than 2 dimensions, you can do this for n dimensions, and it's fine. And that's good. In fact, let's look at just for refresher, let's look at the Euclidean distance page on that. Yeah, thanks Wikipedia. And you can see that exact same formula right there. Whatever your first thing is, whatever your current thing is minus the other thing, squared. So I, in this case, refers to how many variables you are working with. So in a 2-dimensional plane, you have 2 variables. If you've got a 3-dimensional space, you've got 3 variables. Or you might have an n-dimensional space, and you might have a lot of variables. Okay, so that's really great. I mean, that's what the literal planar distance is. If you're working on a flat Earth, that's totally fine. Mahalanobis distance, it tries to fix some problems with Euclidean distance. If you've got, make sure I say this right, if your variables are very differently shaped and your variables, some of them are correlated with each other, then you would kind of like, and you know that ahead of time, you would kind of like to account for that. If most of the distance in this variable is already accounted for in another variable, you shouldn't really add up that distance again like you do in Euclidean. So that is what we're going to try to deal with. We're probably not going to, I don't want to go too much into what it means. Essentially, what we're dealing with here is going to be this formula, or you can look at this formula, same kind of thing. It's very similar to what we had before. Here we're taking the difference. That's the difference in one variable with the other, and you hit it with the covariance matrix. That's sort of telling you what variables are correlated with each other. So in this case, you've got 2 points, as before. You're sort of squaring. You sort of have a squaring thing going on. Here we're doing everything in vector notation. So it's got this transpose, and we're going to hit it with this. And we're stuffing the covariance matrix in the middle. And that's what's going to help us account for the correlations between these variables. So the problem that you're going to have is, where the heck do I get this covariance matrix? How the heck do I make it? Like with Euclidean distance, you've got a vector, you got another vector, or you got a point, you can think about it, and another point, and you can always just, okay, what is the distance between those 2 points? You don't have to worry about it. Here, you need some prior knowledge about the distribution that your points come from. And so that's where you get that information. That's why it's important. If you only have 2 points, well, then maybe Euclidean is totally fine. But if you've got 100 points and you want to know the distance, quote unquote, between two of them, then maybe this is useful. But we'll see how it goes. My intention is to work on this for an hour tonight and come back next week and see where it goes. And if it's going terribly, well, it's going terribly. First things first, though, I would like to make a little bit of data. I think I am just going to manufacture data because I'm a horrible person and that's what I'm going to do. And let's see what we do, how we choose to do that. The more things we can do in TensorFlow, sort of the better, right? I think I might have lost that session. Okay, I've lost this pane in my tmux, which is unfortunate, but I can kill it, and it's dead. DED, dead. And I can make a new one. Proj TensorFlow. Nothing there. Yep. Okay. Maha.py, sure. Import TensorFlow as TF. So it's entirely possible that I won't even get to TensorFlow. That was weird. There we go. But we'll see. I'll try to do more of it in TensorFlow than other things. Import SciPy as SP. Can I do that? Nope. Thought I could. Alright, well, we're going to see if I can install SciPy. I could have sworn I installed SciPy. From scipy.misc, image read. Son of a gun. Alright, let's look up Mahalanobis Distance SciPy. That's how this game is played. Mahalanobis Distance SciPy, because I know there's a distance measure in there. SciPy.spatial.distance.mahalanobis. Let's do that. Do that, import Mahalanobis. Let's see if that works. Nope. Thought it totally would. That's a bummer. Alright, cproj TensorFlow. Source my session, my virtual environment. I'm going to pip install SciPy. See how that's going. Alright. Things are happening. Oh, I might have to sudo. We're going to find out here in a second if it yells at me or if it's totally fine doing it locally. Basically, we're going to be trying to just be comparing against this metric. As you can see, it takes your first vector, your second vector, and VI being, V or VI? Note that the argument VI is the inverse of V. Okay, so you pass it the inverse of the covariance matrix, which gets plugged in there. Interesting that they do U minus V and then U minus V transpose. That doesn't really matter. But this is the metric we're going to be trying to get up to. If it's as efficient, that's fantastic, much better than I would expect. I just want to see how doable this is. In principle, not that hard. The hard thing will be computing the covariance matrix. That's always the hardest thing. We might cheat, we might use SciPy to compute the covariance matrix of a data set. We can always go back and try to fix up that part later. This is still doing stuff. Oh my goodness. Pip, you're killing me, Pip. Import SciPy dot. Nothing. All right. Well, in the meantime, let's get some numpy going on. Numpy as NP. There we go. And I need to generate a random data set. So what's a good random kind of data set to make? Make a horrible list? No. Make a set of arrays. Yeah, I guess that's reasonable. Every row of my array will be an observation. Yeah, numpy dot zeros. How big do I want it to be? Let's see. Num observations. What's enough to start with? 100? 1,000? Start with 1,000. Let's start with 100, just for laying things out. All right, that's the number of observations. How many variables do we want? Var, let's say 5. Yeah, let's say 2, so we can actually visualize everything. Just for getting things started. Numobs, numvar. There we go. Boom. Of course, our data is full of zeros right now, so we need to actually put things in it. Yeah, for I and numobs, I want data of data of I equal no. It's the first variable. Let's see. Let's say initialize data column 1 var column 0 var. Let's just make that in an indicator variable, right? Yeah. Zeros and ones. That's all it is. And column 1, let's make that a number between 0 and 100, and we want to correlate it to 0.99. I like more. We would like to correlate it to column 0 a little bit. Not a whole lot, not 100%. We don't want it to be the same. Maybe later on when we're trying things out, we will do that. But for now, let's just give it a shot. No numpy.random dot, oh gosh, dot randint, right? Let's learn all about randint. Low inclusive, high inclusive. So if I say 1, if I say 2, okay, so numpy.random, int 2 gives me a random bit. Let's save that real quick. Oh, SciPy actually worked. Okay, cool. Whoop, not 20. All right, let's see if we can import SciPy. We can. Okay, excellent. So we can at least test our own results. Let's kill that. Then, what I want to do is say I want it to be numpy dot, not numpy dot random, derp. If it were this, that would be really, that would be extremely correlated, right? Yeah. Let's just say correlated. Plus numpy dot random dot just rand, is that what I want? Yeah. No. Randint 51, I think. Numpy.random.randint. If it's low is actually the high, and high is not included, which is different from how random works. If you import random, it's a random.randint. That's inclusive in both ends, I think. Yeah, so that's something to be careful of. If you're random.randint, that's inclusive in both ends. If you're using numpy, it only includes the lower end. Things to be wary of. Things to be wary of. All right, so at most this value is going to be 100. We're going to have half of it is totally random. Half of it is based on the previous indicator value. So these are going to be pretty severely correlated. Let's generate that data, why don't we? And let me do my auto indent. Int object is not iterable. Right, I need a range. That's a mistake I make all the time. Thankfully, that's a quick one to fix, and the Python interpreter is quick to tell me all the things I'm doing wrong. All right, before we jump into this, I want to actually just look at this data. So I'm going to import pylab as PL. I don't have pylab. I could have sworn I had pylab. cd proj TensorFlow source pip pylab. Maybe I had matplotlib and not pylab. We'll see if he yells at me here in a second. Import matplotlib. No module name matplotlib. Okay. Well, I would have liked to have visualized it. But if it's not going to let me, it's not going to let me. We'll get to that in a second. Something we should be able to do is we should be able to use SciPy to compute the covariance matrix. So let's see how we can do that. SciPy compute covariance matrix. We got a data set now. We should be able to do this. Oh, we can do it with NumPy too. Let's... They probably use the same underlying library anyway. What do we got going on? Parameters. Oh, that's lots of parameters. This is much smaller. M is a vector. Return the variance. For matrices where each row is an observation, each column a variable. Haha! We have structured our data in the correct way. That was actually a guess. Note in this case that diag covariance M is the vector of the variances for each column. Covariance M is the same as covariance M, M. Normalization is by n-1, where n is the number of observations. If bias is true, the normalization is by n. If row var is false, then each row is a variable with observations in the columns. So you can do it the other way. Let's see if this works the same way. Covariance indicates levels which two variables vary together. If we examine n-dimensional samples, yes, then the covariance matrix element Ci is the covariance between xi and xj. Element Cii is the variance of xi. So just how variable is that particular variable? Okay. So if we pass it our array right now, numpy.cov, let me give myself a little more room here. I just want to call it, they call it V. So let's call ours V. numpy.cov of data. See what happens. Boom, we got it. We got our covariance matrix right here. So that's cool. And we can see there are some big numbers in here. You can't really get a feeling for that though without that's not. I feel like you can't get a good feeling for that just from glancing at it. Oh well. Evidently I'm installing scikit image too down here. That's interesting. You can see my home directory down at the bottom. Isn't that fun? Alright, we've got a covariance matrix. That's great. Alright. So that, I guess that's the hardest part. So that's, boom, we're done. Simple. I want to implement this first without using any TensorFlow first, just to see if I can do that. And then we'll jump into the damn TensorFlow. I know that's what people want to see. That's what people like. It's super cool and neat. Actually, tab new. Is this? That is climb on cross entropy. I'm trying to remember when I top 2. All right, cd proj. I'm trying to find what I did last week. You would think it would be right here, you know? TF. Basic. There we go. TF/basic. There we go. Just so I have that and I can remind myself how the heck this works. But this week I'm not even working with a tutorial. I just have my clock. It's counting up. It'd be funny if it was counting down, telling me you have this much time until the hour is up, and if you don't have Mahalanobis Distance working, the Earth explodes. Oh well. Alright, scikit-learn is getting installed. Life is going well. Oh gosh, that M is horrible in this font. It's just a floppy disk. Ugh. Alright, that's fine. Alright, so what are we actually doing here? X is a single observation, Y is a single observation. So X minus Y. Here we go. Is this what I want? If the covariance matrix is the identity, it's not. If it's diagonal, it's not. So this is a vectorized transpose. I'm willing to bet that I can get away with just using a vectorized subtraction in NumPy, and life will be good. We're gonna find out though. Okay. So if it's in X minus Y, which is some kind of row, dot transpose, which I'm pretty sure is the thing you can do. Yeah, there we go. Times, we want V inverse. Yeah. NumPy dot inverse? Is that a thing I can do? Ooh, NumPy dot invert. So that's not the same. That doesn't sound like a gives me what I want exactly. Sorry, I was hoping for NumPy dot inverse and it wouldn't change the thing in place. Let me just look. V dot invert. You can always dot invert it again, right? Has no attribute invert. Okay, that tells me what I need to know. Let's shape. Tuple object is not callable. Well, that's good. Yeah, do not have an inverse operation. That is. Is there a NumPy dot matrix? Is that what I'm missing? V matrix. VM dot. Do I still not have inverse? Really? Alright, now it is time to. Oh, VM.I. Did I have that with V? No. Okay. VM equals NumPy.matrix V. There we go. And then VM.I. Singular matrix. That's bad news. A legal value. Oh boy. I can't invert the matrix. That's going to be trouble. But it's not diagonal. No. There's definitely things on the off diagonal. Let's ask the internet for assistance. NumPy invert covariance matrix, right? Conveniently enough, someone is asking about Mahalanobis distance. We'll save that too. Inverting ill-conditioned matrix in NumPy. That's probably what our problem is. No, our problem is singular. If I remembered my linear algebra from college, this would probably be a little easier. Right. My matrix, it's not even that huge. It's 100 by 100. Always be singular as part of the nature of covariant matrices. This is due to rounding errors and splits. What you're trying to do is not mathematically sensible. 2 variables and 2 observations, you have a scatter plot with only 2 points. It's certain that the covariance matrix is 0. But that's not what I have. I have a whole data set. It's 100 by 100. This is not crazy. Observation of this stuff. Multiple variables and observations. Each row of M represents a variable. Each column represents a single observation of all those variables. Wait. Did I use numpy.conv and it's the opposite of how scipy.conv is? I think that might be the case. Each row M represents a variable, each column a single observation. Curse you! Alright, can I say row var equals 0? If row var is non-zero, then each row represents a variable. Alright, so row var equals 0. Opposite of scipy. Yes. I should have recognized that I was getting a matrix that was way too freaking huge for what I was wanting to do. And this is the stupidest use of scientific notation. This is a quarter. This is 783. This is 12, and this is 12. That's quite silly. Alright, but now we can invert the matrix. Life is good. Let's continue. Let's see if we can just do whatever .i. You know what? Let's make our own little, I want to see the difference between 2 particular points. We're just going to take x and y as our first 2 observations. There's x, there's y. You'll notice significant differences already. Oh, hey. Our PyLab installed. Ding. Let's do pylab.ion. Cool. I want to look at the data real quick. I love to do heat maps. Let's do a heat map. Pylab.pcolor. Data. Module objects. Really? Does Pylab not exist? Pylab is apparently being silly. This is strange to me. Pylab.ion has no attribute ion. Apparently Pylab has no attributes whatsoever, which I find amusing. Kill IPython and make it new. Maybe that's the problem. Alright, so Pylab is not working. Sorry, we still have no visualization then. That's frankly wrong. Am I missing something here? Successfully built. Pylab. I don't think that's true. I think it didn't install correctly at all. I think it's lying liar. Yeah. tf/lib/python site packages. It says Pylab's right there. That's what it says. But you'll notice there's nothing like going with it. It's just a basic Pylab file. Pylab.py. Show me. Yeah, oh, it's it's UTF-8 file. That's useful. What about in this? No. Did it actually install anything? What about the scikit-learn, sklearn? That's another useful thing I was going to learn one day. Okay, that looks sort of like it's there. Support vector machines, do those exist? Yes, those exist. I don't know why Pylab itself failed to install. Install Pylab. requirement already satisfied. All right, I'll say dash dash upgrade. Maybe you're just not thinking straight. Okay, it's doing something. Successfully installed IPython. That's strange because that's not what I asked for at all. Kill that. Open that. Do that. Alright, sorry, we're not going to have PyLab because apparently IPython is being really stupid and doesn't want to pip install things it's supposed to pip install. Alright, wait, one more thing. One more. We'll see if we can just install matplotlib. Pip. Already satisfied. Really. That's cute. From matplotlib import pcolor. Come on, plot. So can I do that? Can I import name pcolor? Import matplotlib. Matplotlib dot. Alright, there are things there. Plot? No, nothing dot plot. Alright, forget it. Forget it. That's all gone. Not what the focus of today is about. We have X. We don't have X. Let me make new data points. Let me make sure I... Boom, we have our new data points. That's our new matrix. You notice still about 2.25, if that makes sense. Still 822, 8, yeah. And 12 and 12. So basically the same data. X and Y are the same here. That's weird. Is that just a fluke? I really hope that's just a fluke. The first 3 data points are the same. That's really strange. I wonder if numpy.random has some bad seeding or something? That's super strange. That's... I'm suspicious, to say the least. Show me again. There's one match. That's not so weird. There's a lot of really similar... like, within the same 50 range. Alright, I'm doing 100 things. There's a couple... right there, again, right next to each other. That's super weird. I don't like that. I don't want to wait forever, though. Time dot sleep. Can I sleep for non-integer number of seconds? No, no, no. Come on. Argument must maybe a floating point for sub-second precision. There we go. Time dot sleep. 0.01, 1/100th of a second. So this whole thing should take 1 second now. See if that's... maybe it was just... so I expect some matches, sure. I don't expect them right next to each other. That's what was throwing me off and I was not liking. Alright. I declare this data to be random. We're going to continue and press on. Alright, yep. 0.24, 928, 13, and 13. Basically the same. It's always good to check to make sure your data is what you think it is, even when you're manufacturing data yourself. So if we get nothing else out of tonight, that was a good thing to look into. Alright. I say x minus y. So I say, let me save this off to variable. xy equals x minus y. And I want xy dot transpose times v dot I times xy. What happens? Not v dot I, vm dot I, the matrix, of course. Whoop. That's what I get. There we go. 1, 2, 1, 2, not aligned. Because xy dot transpose is a 1, 2, and vm.I is a 2, 2. And xy. Oh, I see. And xy is intended to be a column vector. So xy dot reshape 2, 1. There we go. So NumPy treats all vectors as though they have one row and many columns, but really we need to be thinking of it as having many rows and one column. So we will just reshape this as 2, 1 here. Let's reshape it as numVar, 1. Is that right? Yes, because it's a vector. Boom, we get one number out. I want to save that off to s for the moment. And I want to say numpy dots really have a square root. Yes, nice. On s. S of 0, 0. Son of a s of 0. It doesn't matter. We'll just there. Okay. I want to save that off to m. So that is our supposed Mahalanobis distance between these two things. You'll note that's almost certainly a lot smaller than the Euclidean distance. What's x and what's y? Yeah, the Euclidean distance here, that's already like what, 50? Plus one more. 52. You square each of those, 50 squared plus 1 is basically 50 squared, square root. It's basically 50. So this is only 2. Much smaller, because you're already accounting for a lot of the distance. Okay. So let's see how that compares with SciPy's Mahalanobis. We have a matrix already. I'm gonna bet that it can already take the numpy dot matrix. We have x, we have y, we have v m dot I. Boom, we get the same thing. So let us x minus y dot reshape length of x, come on. There we go. Let's see if our function does the same thing. I need to auto indent again because I always forget that. Maha x, y, v, vm even. I forgot square root. Always important to remember square roots. There we go. Boom. We get the same results. We have successfully implemented Mahalanobis distance for outside of TensorFlow. Okay, but that's important to justify to ourselves that yes, such a thing is capable of being done. Let's consider how we're going to do this inside of TensorFlow then. Now that I've got 20 minutes left to figure that out. So we need to break down our computation graph into a couple different things. What do we need to compute? That's really the question. We have to decide what the scope of what we're going to do is. I think for the sake of this, my data will exist outside. I'm going to compute my covariance matrix first outside of TensorFlow for the moment being. And then I really just want to implement this function in TensorFlow. TF Maha. Gosh, that font is horrible. And that is the goal of what we're going to have. So we got to break down We've got this vector subtraction. That'll be something we have to do. We've got to manipulate our vectors into different shapes. We need to take an inverse. If taking an inverse is too much of a pain, you know what? We'll just pass in the inverse. But we still got this matrix multiplication, and we still have a square root to do at the end. So let's see how that really goes. What did we do over here? Always got to go back to the beginning. There's a default graph of some kind, right? Yeah. Ah, no. So let's look up TensorFlow making a specific graph, right? TensorFlow specific graph. Whoops. Oh. Because I don't want, every time I call the function, I sort of want it to be its own little graph right there, right? That's what I think anyway. Yeah, they're on GitHub. TensorFlow disappoints. That's unfortunate. Someone isn't very happy with TensorFlow. That's okay. This is a different looking page. This is a Google source. I don't remember seeing this page before. Okay, anyway. Sesh equals tf.session, sesh.run product, yada yada yada. Yeah, so this is what we did last week. I think if I just make my own session there and I close it. Alright, let's try that. With tf.session. See if I can remember anything. As sesh. So we'll do that with statement because we're going to be using a function. And I don't want to have to remember how to close it. I just want to return and forget about it. All right. So x and y are vectors. How do I deal with that in the context of TensorFlow? I just need to subtract, and I need to subtract element-wise. Is that something I can do in TensorFlow? So I want a placeholder variable for something I'm going to put in. There we go. So we have a couple of placeholder variables, x and y. That is a float 32. I don't know if I can obviously do this for vectors. Let me look that up. TensorFlow vector. Let's say addition, just for giggles. MNIST for beginners. Yeah, addition's giving me things I don't want. Go up by adding difference. Oh, this k-means clustering with TensorFlow I saw. I read a little bit of. That's really cool. That's one day I might take a poke at that and try to add this Mahalanobis distance as the metric in there. So that's pretty cool. Difference. Computation. It's got a difference. TensorFlow, large-scale machine learning. Create a 100D vector for input. TensorFlow, 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 TensorFlow. Just search vector on here. Ah, right. We have this MNIST thing. Ah, right. You can specify the size of something. It's important that I remember these things. None, and this is going to be numVar is simply the length of x. Sure, you can say I'm a horrible person, I should use numpy.shape, but that's okay, we're just learning. Number of variables. Zoom. Okay, that's how you pass in a vector. Right. And what do we need to do? And we need to pass in our covariance matrix. I don't want that to be TFX, TFY. We'll use that naming convention for the moment. We'll see how that really works. That might be more confusing than helpful. You know what? XX, YY. VI, VI. Perfect. Those are what my TensorFlow variables shall be called henceforth. VI, VI is... It's numvar by numvar, right? Yes, that is correct. So, first thing I need to do is take the difference. So diff is xx minus yy, right? I've got to build the graph up first. Yes. You know what? Let's learn if we can actually use things that way, shall we? I want to open up an interactive session right now so I can learn some things. Last one used, sure. I have 4 local threads, that's cool. Local device intra-op parallelism. Local session inter-op parallelism. Interesting. Just kind of neat. And I'm doing this in BASIC because I'm just screwing around. Do some vector comps. Yeah. So let's check out some of this stuff. We'll do 5, 6, 7. You know what? I don't actually care about any of those. 8. None, comma 2. None, comma. See if I spell none correctly. 2. So that's just small vectors there. 7. tf.mul. That's dumb. I'm not going to do that. No. We're just going to do input 7 minus input 8. This is output 3 now. Right, so I'm just trying to see, I'm fiddling around with vector computations in TensorFlow just to make sure I get it right when I actually put it in my function. So I'm going to take some 2 long vectors over here, input 7 and input 8, and just compute their difference. And I want to know what that looks like. So let's find out. Let's make a simple vector, one that's 0, comma 1. This is 7 minus 8. I'd rather not deal with negative numbers. This is 10 and 5. And we will say the other vector is 2, comma 3. Just for giggles. Let's see how that goes. Okay. Then we're going to run that. Input 3 is not defined. Right, of course I didn't define input 3 because these are 7 and 8 now. Just kidding. Can I feed shape 2 into tensor placeholder u, which has shape dimension none, dimension 2. Alright, so I am not thinking about that quite right. mnist gets read into input data. Should I not have none? Is that what I shouldn't have? Just dimension none, dimension 2. Let's try that. Maybe that's the correct. Okay. And yes, you can see 10 minus 2 is 8, and 5 minus 3 is 2. So that did what we expected. So that's good. I want to see one other thing. We can do matrix multiplication. So this is going to be a simple thing. Okay. So now I want to look at a 2 by 2 and a 2 by 2. And we are multiplying. Yeah, no, I shouldn't call them. Should name them different things. 9, 10, 5, comma, I don't know, 1, comma 2. Yeah. I guess I'm multiplying, so I don't really care if it ends up being singular or whatever. I am going to put this over here so I don't go bonkers trying to see things. 4, comma 4. Why not? Okay. Let's see how the matrix multiplication gets handled. Does he yell at me? Does it like, whoa, it doesn't like that. Did I do this wrong? You must feed a value for placeholder tensor with d-type float and shape dim size 2. I think I misquoted what it should be. So I believe I'm using the tensors incorrectly. So let's matrix. Yeah, no, that's a 1 by 2 matrix. That's a 2 by 1 matrix. Oh, matrix multiply. Hey, hey, maybe that's the problem. Actually, did I do this already then? Did I already do a matrix multiply? Am I an idiot? Did I already forget what I did last week? It's entirely possible that I just forgot what I did last week. That make mult. It's a perennial problem. Always forgetting what happens. Shapes must have same rank. Not 7 and 8. Alright, so that was actually probably the problem. Forgot to update these guys to 9 and 10. I'm betting... You know what? It might not do... Well, let's see what it does. It might do element-wise multiplication, which would be 10 times 2 would be 20, 5 times 3 would be... Yeah, okay. So that's element-wise arithmetic, but that's not what we want. We want a true matrix multiply. Do-do-do. So we'll change that. Recompute. And that looks... I'm willing to believe that's correct. Let's just input these arrays and find out. Excuse me. NumPy.array again. Yeah. So NumPy.dot is the shorthand for doing a matrix multiplication in NumPy. If you have like one-dimensional vectors, you can usually get away without thinking about it. All right, so that's cool. And that really worked over here too. Huh, neat. Okay, so our vectors work. As long as I use a matrix multiply, I'll be okay. The m's here are totally fine. Why are the m's over here insane? This font is gonna drive me bonkers. What is the deal? Alright, I don't know why that is the way that it is. Alright, so we have a couple. How can we transpose this correctly? That's going to be an interesting question. And how do we take the inverse in TensorFlow? TensorFlow matrix inverse. That's what we want to ask. Oh, no. I'm passing in the inverse. Never mind. Do-do. Rewind. TensorFlow vector transpose. That's what we want to know. Transpose op. I don't really want to dig through the tensor transformations. That's what I want. Yeah, I don't want to dig through the source code unless I have to. Shape, reshape. It's not exactly right. Is Transpose. Hey, what do you know? Okay. So dt is going to be my tf dot transpose diff. Perm equals none, name equals transpose. Perfect. Transpose is A, permutes the dimensions according to perm. I do not want to permute the dimensions at all. That's quite all right. And ds is going to be, so dt is this business where we're transposing. ds is going to be this business where we just have to reshape and pretend we're in the opposite direction. Right. Diff dot, not diff dot anything, right? Just tf dot reshape. It's very numpy-like. I like this. That's nice. Reshape. This is a good interface. I like this help. This stays up here while I'm searching, but I can click on new things over here. That's good. And it doesn't screw around with this scroll wheel. The little things, you know? What is the tensor? What do I want the shape to be? Okay. So this works very similar to length of x, comma 1, right? I bet I can get away with this. I bet it will do the right thing. Our big multiplication is going to be tf dot mult. Important question, can tf dot matrix mult automatically just do a couple of matrices at once? We're going to find out. No, it does 2 matrices at a time. Okay. Sum1 equals tf dot matrix mult mat mult dt and vv. Right. And then M2, I'm just doing every computation as a separate node, just to spell it out very explicitly. We're going to take M1 and we're going to take that multiplied by ds. And I want my output to be, does TF have square root? Let's find out. Square root. Hey, what do you know it does? A tensor. Perfect. This is going to be tf dot square root of m2. Now, all of this, we have to drill this into our skulls. All of this is just defining what the graph is. It's not actually computing anything yet. To do that, we need our sesh.run, which means I have to remember how sesh.run works, which means I have to copy from my old lines. So we will sesh.run output, and we are feeding in a variety of things. XX. We're going to feed in X. We are feeding in YY, which is going to be Y. We are feeding in VV, VI, VI, which is going to be VI. Okay. Then that will stuff into output. No, that will not stuff into output. That will return. Return is the wrong word to use. That will give me the output number I'm looking for. So I'll just say ants equals that. And then I will simply return ants. All right. For giggles, I often like to just see if functions I write on the first run will actually work. Fully understanding that most of the time, they won't. Again, we've already defined our variables. So, and again, Mahalanobis of our things is this. If we don't get back exactly the matrix format, that's fine. We're looking for this number. TF. So rather than that, TF Maha, we're gonna pass in the inverse. We don't want it to think about how it has to do that. Cannot feed value shape 2. Haha. Which has shape none and whatever. Oh, right. I fixed that over here, but not over here. So that's that was a foolish thing to do. Yes. These are one-dimensional vectors. And I would not be surprised if my reshaping was not actually necessary. Dimension none must have same rank. What is none? That's interesting. Sesh is still going. Okay. Shoot. Sesh, is it open? I think it must be if it has closed. That's what I'm choosing to believe. Oh, didn't like that. Didn't like that at all. Sesh dot M1 it didn't like. That's interesting. Alright, let me just do that line and see what it complains about here. Tensor dimension 2 and tensor shape dimension none. Why is it dimension none? Isn't num var defined? 2. Alright, this is a little... Am I misunderstanding how the dimensions work? Did I not just do that over here? 2, 2. Alright, why don't I... Here, I'll do sesh.run. I want to compute dt... Make sure I do this right. ds dt diff. Just get all those things together. Feed dict is going to be xxx, yy, and vi, vm.i. Do this the right way here. Alright, so I'm going to take a peek at these values and see what it is. I'm already a few minutes over. Okay. That's interesting. Oh, right. Yeah. DT and diff should basically be the same thing. Basically, but maybe not exactly. Those actually look slightly different, which is interesting. Okay. So here we see ds, which is the thing on the right. So that has 2 rows and 1 column. Here we see dt, which has 1 row and 2 columns. And this is diff, which of course has the 1 row and 2 columns because it's just a vector. I actually want to get my hands on VV as well. Placeholder is both fed and fetched. That is a fair point. TensorFlow now. VM.I, that's what I want. So I can't take a, well, that's a 2 by 1. Of course, this is a 2 by 1 matrix. But that's on the right hand side. That's ds, right? Did I multiply incorrectly? No, I matrix multiply here first. And I definitely can, I'm almost 100% certain. DDT, DDS, DDT, DDiff. Okay. Numpy dot dot DDT, comma, VM.I. See, that works. That's what's suspicious here. And this is almost working. So I'm a little perplexed. I'm going to spend a little bit more time on this to try to get this going. 15 more minutes max. And dt and vi are matrix multiplied here. And that is what I've done here. That is the value inside of it. So what was the error again? Sesh.run. Really? That's not what I asked for. Show me M1 as well. M1 is not defined. That's a lie. Oh, I see. It doesn't even want to show that to me. That's weird. All right, maybe I have to tf.sub to subtract. Let me double check that sub is subtraction and not substitution. All right, maybe that's what it's expecting. No, didn't like that either. Why doesn't it like... Is it because it's all... No, numVar is just a variable. Nothing wrong with that. Diff is just a thing. M1 is not defined, right? M1 isn't defined because it's silly. tf.make small dt vi. We'll see if I can do this. I don't think I can. We're gonna find out. No, it doesn't like that, of course. Trying to fool it into giving me what I wanted. Maybe there's something I'm missing about it here. Oh, jeez. Go away. Oh, it does have an inverse function. Hey, what do you know? That's good to know. Multiply. Mate mult. Transpose A, transpose B. A is sparse. B is sparse. Multiplies matrix A by matrix B, producing A times B. Must be two-dimensional matrices with matching inner dimensions, possibly. Oh, is the problem that it's not actually two dimensions? I think the problem is that it's not actually two dimensions. DT is not. Okay. So we need to reshape it as well. And it needs to be 1 comma length of x. Well, let's try that. Let's see what happens. If that doesn't work, hey, that actually ran. What do you know? Recall last time it wouldn't even define vi is not defined. Of course vi is not defined. Because it's vm.i. Everybody knows that, right? Ants. Boom, look at that. We are using TensorFlow to compute the Mahalanobis distance. Boom. Versus Maha. Versus SciPy. Versus this. Boom, boom, boom. Alright, you notice we've got some numerical stability concern. It is a slightly different value. So we could fiddle with these numbers a little bit. I'm not going to do that today. But our basic Mahalanobis distance is working. So we can get a slightly more realistic distance given that our variables are different. And we're using TensorFlow here. Real quick, I just want to time it. See how fast this kind of thing is. Using the built-in SciPy 66.8 microseconds. Using the pure Python version. Well, using numpy.square roots and stuff. That's probably going to be pretty close. Maybe not. Okay, so it's maybe twice as much. And we have not optimized this at all. But let's see what happens with TensorFlow Mahalanobis distance. Time it is a useful routine for getting the vague amount of time. So about 1,000 times slower. The micro versus the milliseconds. Which is not surprising because we spelled out every single computation here. But that's just interesting to see. All right, so that's it. We've got Mahalanobis Distance working. Next week, I might go back to tutorials. I might fiddle with this a little bit more, like get the actual covariance matrix computation done, do the inverse computation inside TensorFlow as well, that kind of thing. But we'll see. But anyway, thanks for tuning in, and I will see all of you next week.